Hello everybody, welcome to our lesson. Today's topic is Faraday's law of induction. This is the goal of the lesson. At the end of the lesson you will be able to describe methods to produce EMF with magnetic field and express Faraday's law of induction in a form of equation. From the previous lesson we concluded that whenever a conductor is placed in a changing magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced, which is called induced current. And this formulation is actually called Faraday's first law of induction. And Faraday's second law of induction is about expressing EMF in a form of equation. And to do that, let's go to PhET simulations and do Faraday's experiment again. In the previous time, when we performed this experiment, we concluded that a current and an EMF were induced due to relative motion between a magnet and a coil. But we didn't pay attention to the characteristics of motion. Does speed of a magnet affect an induced current and EMF in the coil? You see, if I move the magnet faster, the deflection of a voltmeter is stronger. Now let's change a voltmeter to a bulb to have a better observation. Current produced is stronger when the magnet is moved quickly rather than gradually. If we take into consideration the results from Faraday's first experiment, a current was induced while turning the switch on and off. The real reason why current was induced is not the motion of a magnet, but change in magnetic field strength. I can show it here. I will not move the magnet and just let it stay where it is. Instead, I will just change the strength of a magnet. And you see the light from the bulbs and a motion of electrons. Current is induced without moving both the magnet and coil. And note that in reality we don't have any bar magnets that can adjust their strength, but electromagnets can. Next, we will observe if the area of the loop affects an induced current and EMF. Now, let's try to change the area of the loop. So I'm increasing the area. Okay, I've increased the area of a loop and I will move magnet back and forth again. And you see that by increasing the area of a loop, we get even stronger current in the loop. And surprisingly, the current is induced if we change the area of a loop without moving a magnet. Look, I'm not moving a magnet and the coil, I'm just changing the area and we see a short light from the bulb. So, the induced current and EMF depend not only on the rate of change of magnetic field strength, but they depend also on the area of the loop. Do you remember the first lesson of induction? The magnetic field applied to a particular area we'll call the magnetic flux. So we can explain the electromagnetic induction by the magnetic flux. The induced current and EMF is proportional to the rate of magnetic flux change. One more thing, we shouldn't forget the number of loops of a coil. The more the loops wounded, the stronger the current. So here are the methods by which EMF is produced. First method is by moving a magnet or a coil. So we said that relative motion causes an EMF. Second, only by changing the area of a coil placed in the magnetic field we can produce an EMF. I have shown you in the previous experiment this. If we change the area of a loop, the voltmeter also changes. And the third, by rotating a magnet or a coil relative to each other. This is how the generators work, and we will discuss it later. In this lesson, we will try to find an equation to calculate the magnitude of an induced EMF, and to find that equation we need to find factors that affect an induced EMF. And these factors are observed from the Faraday's experiment. And from observations we made from Faraday's experiment, there are few factors that are related to an induced EMF. One of these factors is magnitude of an induced EMF is directly proportional to the change of magnetic field, and the magnitude of the EMF is directly proportional to the change in area. And we can combine this into one, saying that EMF is directly proportional to the change of magnetic flux, because you know the multiplication of magnetic field strength to the area will result in flux. Second, EMF is greatest when the change in time delta t is smallest, that is, EMF is inversely proportional to delta t. Finally, if a coil has n turns, an EMF will be produced that is n times greater than for a single coil, so that EMF is directly proportional to n. So, combining these three proportionalities, we get the equation for the EMF induced by a change in magnetic flux. Here, epsilon is the symbol for the induced EMF, n it's the number of turns, f it is the flux, magnetic flux, and delta f it is change in flux, and delta t it's the time interval. This relationship is known as Faraday's second law of induction, or generally as Faraday's law. From the equation we can conclude the following: increase in the number of turns in the coil increases the induced EMF, and increasing one of these magnetic field strengths or an area will increase the induced EMF, and increasing the speed of the relative motion between coil and the magnet results in the increased EMF. So, Faraday's second law of electromagnetic induction states the induced EMF in a coil is equal to the rate of change of magnetic flux through the coil. And the minus sign in Faraday's law of induction refers to a Lenz's law, and it will be the topic of the next lesson. Well, this is the end of the lesson. If you like it, please subscribe and share. Thank you.